Hello dear students, welcome back to the lecture series on theory of semigroups with course code MMTE 405. Today in this lecture we are going to discuss regular and B classes. First I will try to explain a regular semigroup. As you know that in case of groups, if G is a group, then every element of G possesses an inverse, and that inverse is unique for every A. Then for all A belongs to G, there is unique which we denote by A inverse in G, such that A inverse is equal to the identity of group, which is equal to A inverse A. So it also means that A inverse A is equal to A. If I am multiplying throughout by A, which is equal to, at the same time it is equal to here A inverse A. Let's see it. And also this one A inverse is equal to A inverse because A into A inverse into A is identity. So this is in case of groups. In case of groups, we have this. We have A inverse A is equal to A inverse A inverse equal to A inverse. Now, in case of semigroups, we want to generalize this concept of inverse. First, we will define a regular element. When we call an element in a semigroup S is regular. So let S be semigroup. Let S be a semigroup, and A belongs to S. A belongs to S. We say A is regular. We say A is regular. If there is X in S such that AXA is equal to A, that's the definition of regular element. So in case of groups, every element is regular because for all A there exists A inverse such that A inverse A is equal to A. A inverse A is in case of groups. So that means every every element of a group is a regular element. So in case of semigroup, it may not be true, or it may also be true that there is no any such element which is regular in a semigroup S. And if every element of S is regular, then we call the semigroup S a regular semigroup. If every element of S is regular, then S is called a regular semigroup. S is called a regular semigroup. In case of groups, every element is regular. Therefore, every group is a regular semigroup. Every group is a regular semigroup. So that's the note here. Every group is a regular semigroup. Every group is a regular semigroup. But conversely not true, there are regular semigroups which are not groups, as we have an example, rectangular bands. Rectangular bands are regular semigroups, because in case of rectangular band we have for all AX belongs to S, whereas the rectangular band then AXA is equal to A. This is always true for each A, and for each X in S AXA is equal to A. So that means every element is actually regular. For every A there is X. In fact, it's true for every such x. So this is an example of a rectangular band. This is an example of a regular which is not a group. Why it's not a group? Because this x for each a and for each x. Suppose we have a comma x1. Suppose we have three elements in S. Then a x1 a is equal to a and a x2 a equal to a. So there are two elements x1 and x2 for this particular a. So I did a x1 a equal to a and a x2 a equal to a. So for if possible it would be a group. Then this x1 should be unique, because this, in case of groups, it's actually the inverse of a. We can cancel out these a here. Ax1 equal to a, ax1 equal to identity, x2 equal to identity. So that means x1 and x2, they are actually the inverses of a. But we know that in groups every element possesses unique inverse, so it cannot be a group. It cannot be a group because it is true for each a and each x in S. Ax a equal to a. Let me fix a and let me choose two elements from S. Suppose this rectangular band contains three elements. So a, x1, x2. Then by this identity, because it satisfies this identity, ax1 a equal to a, ax2 a equal to a. So which means, so in case this S is a group, then x1 is inverse of a, x2 is also inverse of a, which is not the case, because in group every element possesses unique inverse. Therefore, it's not a group. It's not a. It's an example of regular semigroup, which is not a group. Okay. Now next we define inverse in semigroups. So it's different from the definition of inverse in case of groups. So let's first define inverse. So definition of inverse, let S be a semigroup, let S be a semigroup, and A is an element of S. Now let me define inverse of E. Then A dash is an inverse of A if A dash belongs to S. If A dash A equal to A, it should satisfy two equations. So in case of regular element, if this is a regular element, then there should be A dash such that A dash A equal to A. That's a single equation is required for the element A to be a regular element, but for this A dash to be an inverse of A, we must have two equations. One is A dash A equal to A, and second is A dash equal to A dash. It's like inverse of a group, like A inverse A equal to A and A inverse A inverse. In case of groups, it's true. If A inverse then inverse of A, then A inverse A equal to A inverse A inverse equal to A inverse. So group inverse, in case of groups, every element possesses inverse, because for each A there is A inverse, such that A inverse A equal to A inverse A inverse equal to A inverse. Now here, this is a semigroup and element A belongs to S, then element A dash is said to be an inverse of A if it satisfies these two equations. A dash A equal to A dash A dash equal to A. So that's the definition of inverse. Clearly, if element A has an inverse in semigroups, then this element A is regular, because for regular we need only one equation, A dash A equal to A. So if A is an inverse, if A possesses an inverse in semigroup S, that means there exists A dash, that is A dash A equal to A and A dash A equal to A dash equal to A dash. So that means this A is a regular element, because we have A dash A equal to A. That means there is A dash in S such that for this A there is A dash in A S such that A dash A equal to A. So which means that A is a regular element. So you can write here every element in S which possesses inverse, which possess an inverse every such element which possesses an inverse like A, if it has an inverse A dash, then that element A is a regular element. Then every element in S which possesses an inverse is a regular element. Is a regular element. Now we see the converse. Suppose A is a regular element. Can we say this A has an inverse? Can we find A dash such that A dash A equal to A and A dash equal to A? So suppose A is regular, then there is X such that A equal to A. That's there. But I want to find such X such that A equal to A and X equal to A. Then I can say this A possesses an inverse. So let me try this. If A is a regular element, how can we find its inverse, semigroup inverse? Okay. The semigroup theoretic inverse, not the group theoretic inverse, because in case of groups we have inverse. The definition of inverse is actually this. But in case of semigroups, definition of inverse is this. So they are different. But group inverse is always a semigroup inverse. Converse is not true. You can see it. See this why converse is not true. So we have a number of examples where the semigroup possesses inverse, and it has also an identity. Also inverse, every element has an inverse, but still that semigroup is not a group, because that inverse is not this according to this definition. It's actually as per this definition, semigroup theoretic definition. And that we'll see later on. So let's see this. Suppose is a regular element. Let S be a semigroup. Let S be a semigroup, and A is a regular element of S. We try to find its inverse. Since A is regular, then by definition there exists X in S such that AX A equal to A. So this. Now let's try to define its inverse. Define A dash equal to X AX. We see that this A dash is an inverse of A. Then A dash A equal to A dash means X A X into A. This AX, or you can say AX is AX into AX. You can see it here. AX A equal to A, or you can directly apply it here. AX A equal to A. This one equal to A. It's AX A. Now again apply the same equation. This is equal to A. So A dash A equal to A. Now we see this A dash. It should be equal to A dash. So let's see this. A dash. What's A dash? It's equal to X AX into A into X AX. Now see this. AX A equal to A. It's equal to X. This one, it's equal to A. Now X A X. Again, you can see this AX A. This one, AX A is equal to A, and X A X. X A X is A dash. So that means A dash A is equal to A dash A dash is equal to A dash. So therefore A dash is an inverse of A. A dash is an inverse of A. A dash is an inverse of A. Okay. So if S a semigroup with is a regular element, then this A dash possesses an inverse. There are some examples of regular semigroups which are which are not groups. Example, you can see these example on Aniya book, fundamental book on semigroups. The semigroup of full Tx, the semigroup of all transformations or mappings. It's called full transformation semigroup. All transformations on X is a regular semigroup. Is a regular semigroup. In fact, it's actually monite. So it is an identity, and every element of Tx is regular. So therefore, every element of Tx possesses inverse. Therefore, every element of Tx possesses inverse. But Tx is not a group. Every element has an inverse, and Tx is it also contains identity. It's an identity mapping, but it's not a group. So it's an example of regular semigroup, and in which every element possesses an inverse, and Tx also has an identity, but Tx is not a group. It's not a group. So we know that why it's not a group, because it does not possess group theoretic inverse. For any map which is not bijective, that map does not have an inverse, group theoretic inverse. But every map, whether it's bijective or not bijective, every map possesses semi-group theoretic inverse, not group theoretic inverse. So let's discuss now some regular T classes, properties of regular T classes. We will see that we have to check now structure of regular T classes. We'll see this the properties of regular T classes. Okay. Now, first exercise that which if let S be a semigroup, semigroup is fixed actually. Let S be a semigroup and is regular element, and is regular element. Then every element of L class of A or R class of A is regular. So that means if L is in L class, and if this L class we have one element in L class such that only if you can see there is an element in L class which is a regular element, then every element of L class is regular. Suppose we have L class of any element A or any element X. It has say 100, 1000, any number of elements. It may contain infinite number of elements as well. And if we can locate an element, say A, which is regular, then every element of L class is regular. So every element of L class of a regular element. Suppose A is here Lx and this is regular, then Lx is same as La. So which is simple. So I'll write here La. So if A is a regular element, then every element of La is regular. If this Lx, it has only one, you can locate only one regular element, then you don't have to verify this regularity of the other elements of this Lx. You can directly say that every element of L class of X is regular, or every element of L class of A where A is a regular element. Okay, let's try to prove this. so let B be any element of L class of solution. Let B belongs to LA. Then by definition, then there exists U comma V in S1 such that it's L. L means this U is on left side. U A is equal to B and B is equal to A. Now we show that this B is also regular. Since this A is regular, since A is regular, so therefore there exists X in S such that AXA is equal to A, because A is regular. So let's try to see this. We need to show that B is regular actually. Let's try to find this B. What's B actually? B is equal to UA, and what's A is equal to AXA. Okay. U is AXA. So what's this UA? What's UA? UA is B here. It's equal to BXA, and BXA. Okay, it's BXA, and B. I want this B on that side. How can I do this? What's A? Yes, A is equal to BB. BXA is equal to BB. So it's like this: BXVB. So B is equal to BXVB. So that there exists XV as thus there exists XV in S1 such that B is equal to BXVB. So which implies B is a regular element. B is a regular element of LE. So every element of L class of A where A is a regular element is regular. And similarly, therefore, every